Welcome to the Beer Taster's Notebook, the show dedicated to learning about beer. I'm Jonathan Thompson, advanced cicerone, beer judge, home brewer, and beer writer. Welcome back to the Beer Taster's Notebook, episode 5. So today we're going to be talking about fan. It's a term that's thrown around a lot in beer books without really a lot more explanation. If you're lucky, a pair of parentheses will contain free amino nitrogen, because that's what it is. But there's not a lot more elaboration in general. So obviously in bigger brewing manuals and such things, you're going to get, you're going to get more detail. But for the most part, they just kind of throw it around like it's a term you're supposed to understand. So let's get to it. So what it means, fan, is all of the nitrogenous compounds in the wort. Clear, right? Okay, so nitrogenous compounds in this case refer to proteins and the little bits of proteins. So just to start, the smallest bit of a protein is called an amino acid, of which there are 22. Well, actually, there's hundreds, but there are 22 within the genetic code, at least that we're aware of at this point. And there are 21 that are common to all life forms. So these are called the proteinogenic amino acids, of which 20 are standard, and the two remaining require special translation mechanisms. Proteinogenic means that they're used, of course, to build proteins. And so the 20 are what we're really concerned about. And of these 20, 9 are considered essential amino acids. So essential in this case doesn't mean, well, it means that they're needed, but it also means that the organism can't synthesize them, or at least not quickly enough to be of any value. Of these, valine, isoleucine, methionine, leucine, phenylalanine, tryptophan, threonine, histidine, and lysine. And then of those 9, valine, isoleucine, and leucine are what they call branched-chain amino acids. They're very popular in strength training supplementation and a topic of debate as to their uselessness or usefulness as a as a supplement. So this just means that the carbon backbone has carbon branches, branching off. And so those are the amino acids. So peptides are strings of amino acids up to 50. After that, they're called a polypeptide. And the lines get a little bit blurred here, but once a polypeptide becomes folded and then functional, it becomes called a protein. So if you want to just think about it like this, a polypeptide is a big, long string of amino acids. And then once it folds into a 3D shape and has some functionality, it's called a protein. And so also included in fan are certain degraded proteins, and ammonium ions, which are only sometimes considered, the ammonium ions, that is, and it depends on the method of measurement. So ammonium ions are essentially ammonia, which is neutral and has a chemical formula NH3 that has accepted a proton, changing it to NH4+. This is a key nitrogen source for building amino acids during early fermentation when the yeast is metabolizing it into glutamate. It's also essential in glucose transport. But at high levels, if there's a dearth of potassium, it can become toxic to the yeast as it can start to enter potassium channels. Okay, so FAN is the level of amino acids plus small peptides plus some degraded proteins and sometimes ammonium ions. So that's the most concise definition. The level of FAN in wort is primarily dependent now on malt modification. So during the malting process, endosperm proteins are broken down by endoproteases, which means they're endogenous protease enzymes, and carboxypeptidases, which liberate the single amino acids from those peptides. The higher the modification, the more the FAN level, the higher the FAN level. Mash temperature matters too. Protein rests, which frankly are rarely used nowadays unless you're using really low protein barley or a boatload of adjuncts, is between 45 and 55 degrees centigrade. Some Belgian beers do use this rest because the end goal is an extreme level of esters, which require higher levels of FAN. We'll get to that a little later on. And also just as a side note, the ideal pH range is about 5.2 to 5.4 for a protein rest. So why is FAN so important? Well, if it's too low, then slower or stuck fermentation can result. Poor attenuation, so under-fermented beer is also a consideration there. Higher diacetyl, which is that buttery kind of taste and smell at lower levels and can start to be kind of slick at higher levels. And it is common in certain beers, but generally it's not something you want. And you definitely don't want it at high levels. It's disgusting. Lower FAN can result in higher fusel alcohols and other stress markers from the yeast as well. Also, if the FAN's too high, the yeast will get stressed as well, which means higher fusel alcohols, more esters, increased Maillard products, and haze. So haze from the proteins attaching to the polyphenols can be a major issue as well. So despite the levels of FAN being the focus of most casual conversation, the composition is probably the most important. So the most abundant amino acids in barley are glutamic acid and proline. As mentioned, the malting and mashing process cause a lot of changes, and so the resulting typical wort still has high levels of proline, with aspartate, phenylalanine, leucine, and arginine coming in behind, but alanine and valine are present enough, but the amino acids like tyrosine end up almost appearing in negligible amounts. And probably that's not particularly interesting or majorly important for our learning purposes, but what is important is how the yeast is going to use these compounds. And so yeast use amino acids for protein synthesis, redox balancing, anaplerotic reactions, fusel alcohol production, cell wall formulation, and stress protection. So just to clarify some of those things, so redox balancing just means controlling NAD plus and NADH with NADP plus and NADPH cofactors, kind of like deciding between respiration and fermentation, which we might have to get into in another episode. Well, actually, we will when we do the whole thing on yeast and yeast metabolism. So anaplerotic reactions essentially replenish intermediates in the citric acid cycle, or the Krebs cycle as it's called. And once again, we'll get into that when we do yeast. And so the preferred method of getting amino acids into the yeast is via transport. So there are around 20 different permeases, all which transport proteins in yeast. We can break these into three general families. The general amino permease, GAP1, is the wide range permease. It pretty much allows pretty much everything in, and it works on a host of substrates. So when nitrogen is low, it's active, and when nitrogen is abundant, it kind of shuts off. The second family is the ammonium transporters, MEPs 1, 2, and 3. These are active if ammonium is present. And then the third family are the specific permeases for which each amino acid family has a unique transporter. AGP1 transports arginine and glutamine. BAP2 and 3 work on the branched chain amino acids. DIP5 works on the acidic aminos like glutamate and aspartate. And PUT4 works on proline. Actually, we should talk about proline for a second. So as mentioned, it tends to be the most abundant, but it can only be utilized in an aerobic environment. So the enzyme proline oxidase requires oxygen molecules as an electron receptor. And so low to no oxygen environment basically shuts that enzyme off. Okay, so the amino acid uptake is regulated via a process called nitrogen catabolite repression, or NCR. Yeast have a quality preference scale. So ammonium ions rank first, followed by glutamine, asparagine, glutamate, and the branched chain amino acids, and then the aromatic amino acids, and then the famous proline is basically last. So GAP1 shuts on and off depending on availability, as mentioned. So in a nitrogen-rich environment, it's off, and the specific permeases are turned on for their preferred sources. So in a low nitrogen situation, GAP1 turns on, and the yeast just starts taking in and eating pretty much everything it can find. And if absolutely needed, the yeast can biosynthesize certain amino acids. This, of course, costs energy in the form of ATP, and so import is preferred. If there is a situation in which there's a major imbalance or nitrogen is low, the yeast will break down amino acids for carbon and nitrogen via catabolism. So a simple way to look at this maybe is ammonium an option? Yes. Okay. So if yes, then NCR is active, GAP1 is off, amino-specific permeases are activated, cell growth is rapid and low stress, and the production of fusel alcohols and by extension esters are reduced. In other words, a clean fermentation, which is sometimes what we want. Once those sources are depleted, then the secondary permeases turn on, pulling in the branched chain amino acids. This increases fusel and esters somewhat. And then once those get exhausted, then we start scavenging for nitrogen. So Kveik strains are excellent scavengers, by the way. This is basically starvation/survival mode. And now the yeast is trying to eat everything it possibly can. GAP1 is upregulated and the stress products kick in. Sulfurs and aldehydes, for example, are going to start to spike. So back to the beginning again. What if the answer is there's no available nitrogen? Well, then NCR is inactive and GAP1 is flipped to on. So now the yeast will import all amino acids, even the ones they don't really want. This boosts stress, and the metabolic products that go along with them start spitting out. And so this is going to, this might be desired if you want a really estery beer, but generally you don't really want your yeast to be stressed, right? I mean, we love yeast and we want to take care of it and we want it to be happy and we want it to do what we ask it to do. Okay, so once the amino acids have entered the cells, what happens? Well, aren't you glad you asked? So I think I want to keep this fairly high level and then cover the complex details when we start doing episodes specifically on yeast. I mean, let's see if I can control myself. So the amino acids enter the cells via permeases. We've already established that. And then once inside the cytosol, transamination takes place. So aminotransferases, glutamate dehydrogenases, and aspartate aminotransferase enzymes swap amino acid groups between the amino acids and alpha keto acids. So the goal here is to mostly manufacture glutamate and glutamine along with some other amino acids. The alpha keto acids are transformed into fusel alcohols via the Ehrlich pathway, and basically it gets decarboxylated to an aldehyde and then reduced to an alcohol, and this whole situation can get quite bonkers and probably makes no sense without a visual, so maybe I'll leave it here and do a video. So maybe let's talk quickly about malt contribution in general. So yeast strains, and then why FAN matters in flavor. Right? I think that's probably a good idea. So wheat malt is going to be the highest contributor to FAN, and it's especially rich in valine and alanine. Munich malts tend to be higher in leucine and some of the aromatic aminos. Vienna is pretty balanced, actually. Rye has a lot of soluble nitrogen. Pilsner malt tends to be pretty good overall, but sparse in the branched chain amino acids, and two-row pale malt is pretty balanced. Now, obviously, this differs from barley to barley and maltster to maltster, but those are just sort of generalizations. Adjuncts like corn or rice have pretty much no FAN whatsoever, and then the really dark roasted malts are very poor contributors, and that's mostly because the heat will denature those proteins, so they just basically unfold and become, well, they're no longer functional. So ale strains, it's just talking about the yeast now, ale strains tend to take up the branched chain amino acids a little bit faster, and that obviously contributes to more esters, as we alluded to earlier. Lager strains seem to prefer simpler carbon aminos, and they do produce fewer byproducts, as we know by the nature of lagers. Lager strains also have pretty good control via NCR, and they're much more sensitive to low FAN situations. And then Kvike strains, as I mentioned earlier, are pretty good scavengers, and they're much more tolerant of lower levels of FAN. Okay, so just on aroma and flavor, I mean, I think this is probably what we care about the most. So leucine contributes to isoamyl alcohol and therefore isoamyl acetate, which is that signature banana aroma in Weissbier. Valine creates isobutanol and then isobutyl acetate, which is kind of floral and fruity. Isoleucine makes active amyl alcohols and can be esterified into amyl acetate, which is kind of a pear slash fruity aroma. Then on the sulfur side, so methionine creates methionol, which can convert into methanethiol rather, and DMDS and DMTS, which they smell like cabbage. So you probably don't want that. Cysteine is the thiol precursor that can be liberated into those grapefruit, passion fruit, gooseberry, and sort of cat pea aromas. The ones that are really typical of New Zealand hops and incidentally of Sauvignon Blanc. And of the aromatic amino acids, which by the way, they're labeled like that because they have an aromatic ring as part of their structure. So phenylalanine makes phenylethyl alcohol, and then phenethyl acetate, which has kind of got that rose or honey-like character. Tryptophan can make tryptophol, which is a kind of a vinous aroma, actually. And I mean, there's a lot more, and but some of them are just so minor, and those are the major ones. So I think that's a pretty good place to finish this. I mean, hopefully that's clear enough as an overview of FAN. I mean, as I said, these topics can get really complex, really defragmented, and sometimes it's really hard to stay on the rails with giving complete explanations and without throwing terminology out there that then needs more explanations and more explanations, like a branch chain explanation. I will leave it there. Until next time, stay thirsty and stay curious.